My name is Reggie Chandra and I'm the founder of Rhythm Engineering. My career started as a traffic engineer for the city of Springfield. My first job out of school. Undergrad in civil engineering, master's in traffic engineering from University of Florida. Since that time, we're talking 1993. Since that time, when I was working with the city of Springfield, till now, all I've done is optimize synchronized traffic signals. The number one phone call I used to get when I was in the public sector was this: why am I waiting on the side street when there is nobody on the main street? And I will try to explain. It's because there is a hold on the main street once the side streets are gapped out. Now, you know as well as I do that the motorist doesn't care about the limitation of our hardware. To them, they're just wasting time and gas, polluting the air, waiting on the side street when there's nobody on the main street. The second phone call I used to get was this. It skipped me. I waited on the left turn for 15 minutes. And you would say, oh, signal is in transition. Here also the motorist didn't care what transition was. All they experienced was that they got skipped and they waited on the left turn. The analog architecture of the traffic signals is the culprit for these phone calls. The latest and greatest controllers that we have right now are what I call as electromechanical controller emulators. They are solid state, digital on the outside, but on the inside, all they're doing is emulate an electromechanical controller. The essential components are the dial that turns around once so often, which we call as a cycle length. Then the dial has spins in it that trigger relays that gives you the split, the green splits. Then you have one fixed point in the dial that you can reference an offset to. Let's look at the modern controllers. They are solid state. Some of them are capable of running 120 timing plans, except if you were to run any more than 5, 6 timing plans, you go into what I call as transition hell, which is the signal just goes into chaos when it's switching from one plan to another. The moment you say dial or cycle length, split, force off, or yield point or one fixed point where offset is a reference, the moment you say these three things, all you're doing is you're emulating an electromechanical controller. In 2005, we formed Rhythm Engineering, and in 2008, our solution InSync was rolled out. Here are the three components of the InSync model. One is we convert the analog controller operations to digital. And then the second one is we have a local optimizer that looks at the intersection and optimizes the intersection. And then we have a global optimizer that looks at the entire intersection network. Let me talk about the first module, which is convert analog controller operations to digital. As a solution to this analog sequential architecture is that we have a plugin that makes the analog architecture into a digital state machine. Now, what is a state machine? This concept has been around for decades, more than 50, 60 years. The metaphor is this: an analog system is like your old TV, where if you wanted to go from channel 7 to channel 10, you have clicked your way through. Now, in a state machine, which is a modern remote, if you wanted to go channel 1012, you just punch in the number and it goes instantly to that. There's no linear sequential movement. Here is how we digitize the traffic signals. A state in a state machine is defined as a pair of concurrent phases. Any two phases that can exist without conflict. For instance, on the top left, I have the northbound left turn and the southbound left turn. That is a state. In a digital architecture, I can call it a name. Here, I'm going to call it A1. And any time I want to bring up A1, I can do that. If I want northbound through and southbound through, state F1, if I wanted that, I can call it. And it's going to show up just like punching the buttons on your remote on a TV. So you have 8 states, which are the phase pairs, and 16 sequences. You can have less. Like for instance, if you say that in your city you don't want to have lagging left turns, for example, the sequence E goes away, sequence B goes away, sequence D goes away, and the state machine has to pick from any one of those depending on actual demand out in the field. No common cycle length, no transition, no wasting green time by dwelling on the Main Street green. You serve the traffic purely based on demand. Let's look at the local optimizer. So in our system, we have a camera that is facing every approach. And these cameras determine the queue length at every lane. As cars approach in, it recognizes the cars, and we keep a running count of how many cars are waiting at the intersection. Now, the way we do that is that we draw detection zone along the contour of the lane as far as the eye can see. Then we subdivide those detection zones into segments, which are approximately the length of a car. And we count the number of segments, and therefore we get the number of cars that are waiting. Imagine a person standing at the intersection. He's got tokens that he's required to hand out to each car as it approaches the intersection. And he's also required to give the tokens if a car waits 5 seconds. The car on the left turn, it pulled up, gets a token, waits 5 seconds, gets another token, waits another 5 seconds, gets another token. So as you can see, as cars approach in the video, the token count increases for each lane. This person that is handing out these tokens, he's greedy. He does not want to hand out tokens. So what he does, or what this algorithm does, is changes the lights to minimize the number of tokens given out. We are optimizing for the number of cars that are waiting and the duration of their wait. So a quantity, which is volume, and delay, which is the time it has been waiting. And changing the lights to make traffic flow efficiently. The algorithms in InSync and InSync Tesla are the same. The only difference is in the way in which we determine the queue at the stop bar. Both models are equally effective. So that is the local optimizer. What we do in the global optimizer is that we create speed lines throughout the corridor. On the bottom, you have speed line 1, the green line, which is northbound direction. The orange lines are the southbound direction. I'm assuming that it's uniform speed. In reality, speed changes between segments. What we do is over time, we generate speed lines. So if you are a car and you're traveling at speed and you're close to the speed line, you're going to get all the way through. At each signal, the InSync's global optimizer serves the coordinated movement to progress platoons of vehicle through the time tunnel. Then InSync turns control over to the local optimizer to intelligently serve the best phase combination or phase pair and green times based on real-time actual traffic demand. Here is the entire model. If you had the power to turn your coordinated movements green when you wanted them to be green, and rest of the time the signal ran intelligent actuated, that is the model. We appreciate your interest in the InSync model. For more information on InSync and studies of its benefits to communities, please visit our website. Thank you.